All right, well, good afternoon, everyone, and thank you, Thunderhead, for the invitation to come speak. So I am talking on the subject of validating a Simulex model. Simulex is a partial behavioral egress model. The model itself is validated. The questions I go through regard case studies where unmodified, I don't know that the results of that scenario would be valid. So we'll talk about what does it take to have a model scenario be valid. You need to consider the evacuation conditions. Certainly the software itself, is it validated? We'll talk about the Simulex algorithm and how it would play into the scenarios, how you select the occupants, the geometry, and then we'll hit some case studies. So the first component is, how was Simulex validated and what are the simulations that we're going to be running? So we're going to account for the type of occupants, kind of the general environmental conditions, and then how those occupants move. So with the occupants themselves, we need to think about, is it a partial evacuation or a full evacuation, and how was the model validated? In the model itself, are we looking at a smoke-free environment, or are the occupants observing and accumulating smoke layer, or are the occupants exposed to near tenability limits? I think that depending on those conditions, the behavior of the occupants could be impacted. Whether it's just a typical nuisance alarm, they may not be as motivated to move. If they observe fire cues, they may be more intentional in their motions. And as it nears tenability, we might see more frightened and irregular behavior. And that starts to get into, how do we define what is panic? So with regard to the validation of Simulex, they used video imagery and incorporated that into the partial behavioral model to account for body twist, the acceleration and deceleration, overtaking maneuvers of occupants in a group. I always see myself when there's a group of people and somebody runs from the back to the front. Speed fluctuations and maintenance of interpersonal distance, or kind of jockeying when they're in a queue. There were numerous validation studies looking at footage from department stores, office buildings. You can read the list. And there's also some simulations where they constructed specific geometries to test the model. So one example, which was conducted in New Zealand, they looked at a one-story building. This was on a university campus with nearly 300 occupants, and Simulex and the predicted time from that model is nearly identical to the actual time that was observed from a fire alarm. It was a drill, so there was no fire cues, so we can kind of understand perhaps the motivation of the college students in their evacuation. And then I just put it at the bottom, show the International Building Code requirement of 1.5 times that duration. And as we go to look at the different examples, how that plays in. So now from a 1-story to a 5-story, we see that Simulex, in this case, slightly underpredicts the actual travel time. The occupant load is higher, there are stairs involved, but the model starts to make a bit of a gap, but still very close. And with an 8-story building, the Simulex time is further underpredicted, but with the International Building Code safety factor, the required time is still provided. So how does Simulex maneuver the people? It looks at the building geometry, which is user input, and then it divides that geometry into 20 centimeter by 20 centimeter grid cells. Unlike FDS, we don't have control over those grid cells. We don't know exactly where they land, which we'll talk about in our case studies, how that can be challenging. From those grid cells, it creates a distance map. So it basically draws lines, ISO lines, so to speak, where every meter it shows how far away from an exit occupants would be in the space. Then the user inputs the number of occupants in the space. and Simulex commands every occupant to follow the shortest path. So here's an image of what the distance map looks like. So the exit is here at the bottom, and then the rings, it's like throwing a stone into water. You can just see how the rings propagate from there. So every occupant is going to travel from whatever their position is, perpendicular to the rings of the distance map, following the shortest path. One of the things that happens is because they're commanded to follow the shortest path, the occupants have an inability to become unstuck. So if there's a geometry condition or conflicting body movements where competing occupants have the same drive to follow the same path, it can be created what they call log jams. So who are these occupants? The population group is defined by the user. There's, I think, a selection of 8, whether it's males, females, schools, office populations, elderly. That's pretty typical. The location of the occupants, of course, you can't place them on a boundary of your geometry. They need to live in the distance map. Okay, so how do we build the geometry? So we can't just import the raw geometry similar to the presentation we saw earlier. There's some refinement that needs to happen. And then beyond refinement, there are some alterations and then potentially iterative modifications that are appropriate. So the refinement could be automatic. In Simulex, every line is a barrier. So where a door swing is shown, the arc of that door would be a barrier. So Simulex will automatically remove those kinds of barriers. Other refinements might be manual. And we'll look at some examples in the case studies. Places where alterations are appropriate, similar to the presentation earlier, aisle width can be a challenge in Simulex. People don't sidestep, they want to walk perpendicular. And then narrow gaps can also create places where occupants get stuck. And then the iterative modifications are things that the designer would discover as they work through the modeling process and start to realize how the occupants are behaving according to the way that Simulex commands them. And so you can start to modify the distance map. Okay, so all of those words, we'll start to put them to pictures now. There are 2 projects that we'll look at. One is a multi-purpose arena, and in that arena there are 3 different scenarios, and then we'll look at a theater that has some tiered seating. So in the arena itself, we'll look at trade shows, a sporting event, and a concert. These create different barriers to the occupants, different occupant loads. So here's a trade show, well attended. There's 5,000 occupants, evenly distributed, and there's an exit there, and here. I've not shown the distance maps because it gets too busy. So what we can see is that there's a distributed population and they're generally free to move, which is much different than a sporting event. So here we have some bleachers. One of the challenges with bleachers is the exits are on the sides, and like on the airplane, the nearest exit might be behind you. But in this case, the occupants will tend to move laterally through their rows. And so this center aisle would not be used for an evacuation because it's not along the shortest path. Well, that's illogical, so we can fix that. There's a gap here near a door. That can create a problem for occupants who think that's their shortest path, but then they don't fit. So we have a concentrated population with restricted movements. And so how do we overcome these challenges? Well, we can divide the grandstands by putting in lines to force the occupants to use the aisle nearest them. We can close off small gaps, similar to what we heard can happen with Pathfinder. And in order to cause occupants to use all the available exits, we can add these channelizing barriers so that these occupants no longer have access to this exit. They perceive their shortest path to an exit to be around the back of the grandstands. So how do we justify that? Well, it requires engineering judgment. We're reducing the depth of the bleachers, which is increasing the aisle width, or the row width. And we're limiting the travel in a seating row. And with the case of those channelizing barriers, we're, in a sense, inverting the exit access so that those occupants seated near the exits on the sides are not using those, they're traveling to the back. In a concert arrangement, just kind of skipped ahead to where you can see we've put in dividers so that occupants can't travel laterally through the rows. We've put in some other barriers to force occupants to travel to a certain exit. So with this project, it is an inflated dome structure. And so the purpose of the analysis was to figure out the duration that different exit doors were open, so that if the fans shut down that were used to inflate the roof, would the occupants be able to evacuate before the roof fell to too low of a level? So as we step through, we can see the occupants moving out of their seats and into the aisles. So we can start to see queuing happening. And then depending on the travel distance, there are some queues that have not formed because the occupants have a longer distance and haven't reached their exit yet. Something that's struck me was how we start to see queues forming around obstructions, and then just a thin stream of occupants coming through. There's been studies in Japan that talk about if you have a barrier near an exit, it will reduce conflicts and improve efficiency. But in Simulex, it's a barrier to the most direct path, and so we don't gain the efficiencies that those researchers saw. It results in inefficiencies. And as time progresses in this model, we see some inappropriate things. Perhaps we wouldn't expect queuing here when these occupants wouldn't need to wait in line if that barrier were not there. But if we remove that barrier earlier in the analysis, these occupants would follow the shortest path to an exit, and this queue would be very large. So by forcing the occupants to go this direction, while we never see the queue here, we could presume that if this queue were larger, those same occupants would ultimately end up at this exit. And similarly, we can see that perhaps these occupants would not wait in line, they might come back this way. So I think, again, it's an example of what was the purpose of the model, and we're not so concerned with the location in the building. With each occupant, we're concerned about the duration the exits are being held open, which causes the roof to deflate. Okay, so in order to make that judgment call, to validate that model required engineering judgment. We, again, forced occupants to certain exits, and we had to reason through queuing in the absence or in the presence of other available exits. So here's our tiered seating in a theater. So basically, these zones sit on top. There are multiple stairs that connect each aisle. Well, there's one stair per aisle, and those connect into this area of the lower level. You can see that in the seating area, there's large sections of rows that are missing because of the arc of those rows, we were unable to fit all of the occupants in the seats. And I believe it was probably due to the stagger of the grid cells. So we've left the row ends to help channelize the occupants as they enter the aisles, but left voids in order to accommodate the number of occupants that are present. So as they proceed to their exits, we can see again, the aisles quickly fill, and we start to see queuing. So this is the main entrance. This is also a street front exit. But I think because of the unique geometry of this space, occupants would be well aware of this exit. And because there's these barriers where the occupants are leaving the auditorium that naturally splits the flow, we could have security personnel or ushers that are helping to direct the egress. Here's another example where there might be excessive queuing, which could lead to conservative results. Without this barrier, occupants might naturally go around that column to exit. Other things that happen in this model are we see that there's no resistance here to occupants being able to leave, but we see occupants still remaining up in the tiered seating space. And as time progresses, we'll see that they continue to stay in their aisle. It's a situation where there was conflicting body movements that became stuck. So what we are able to see is because of the symmetry of these rows that did exit and those that remain congested with occupants, we can know about the additional amount of time that we should allow. So we're able to validate the results by using engineering judgment to justify deleting some seats, limiting the travel within the row, again dividing to force occupants to their nearest aisle rather than traveling through the row to the nearest exit. We forced use of certain exits, and we've accounted for jams. So we have to look back and remember that the way that the model was validated was through video footage of lecture halls or other similar arenas. So there's some justification there to rely on the results of the model. We're assuming that there's an absence of panic because there's an orderly exit, and we're able to remain ahead of the developing smoke layer. So with regard to what we did find, there were certainly challenges with the stairs in Simulex. There was a study that was done here in Maryland where they found that whether they used multiple segments of stairs or a single continuous stair with multiple entrances, Simulex would give different results. So I think stairs are something to look at. The effects of the pillar at the exit, what we've read about in Japan and what we've seen in Simulex don't seem to align. And then consideration to changing the movement speed based on whether there's fire cues or not. So, thank you.